Okay. Hello, everyone, and welcome to our session. My name is Natarajan. I'm Senior Director of Product Marketing at Neo4j.
And I'm Jesús Barrasa. I'm the Head of Sales Engineering in EMEA.
We're very pleased to be here today, and we're presenting on a universe of knowledge graphs. So, I'm going to start off with a little bit of background on knowledge graphs. Knowledge graphs have been around for a very long time. In fact, we're celebrating the 50th anniversary this year because the term knowledge graph was coined in 1972. But they languished in the academic world for a very, very long time. And it's only of late that they've become the technology du jour. And there's a reason for this. What we see is what we're seeing is that there's a convergence of analytics, data science, machine learning, and AI, and they're all pulling the need for knowledge graphs. And knowledge graphs they're all pushing the need for knowledge graphs, and knowledge graphs are being pulled along with this momentum because they have the ability to make each of these technologies better, smarter, and most importantly, much, much more predictive. Okay, so with that, of course, the question is, what the heck is a knowledge graph, right? If you Google the term knowledge graph, you'll find that there are over 100 definitions. And it's not surprising because every organization has their definition of a knowledge graph. So let me start off with the Neo4j definition of a knowledge graph. And it's an interconnected data set that's been enriched with meaning so that we can reason about the underlying data and use it confidently for complex decision making. Okay. I know there's a lot to this definition, and you're probably wondering, what is she talking about? So let's unpack each of the elements that go towards the creation of a knowledge graph. Okay, so we have, every Neo4j knowledge graph has 3 elements. We have data, we have graph, and we have an organizing principle. And I'm going to talk about each of these elements in greater detail. All right, first of all, data. Today, data comes in many shapes and sizes, okay? And if you really look at it, data is no longer simple. We're living in a world where data is complex. There are many, data is hierarchical and recursive, and we also find that data could be hidden, right? So that's just one aspect of it. We all know that in organizations, data is stored in silos, and there are relationships amongst the data in these silos, which when harnessed, can really provide very valuable information. And then last but not least, the pandemic. Of course, we have to talk about the pandemic. What has the pandemic done? Before the pandemic, we were all talking about big data. It was big data this, big data that. Today, big data is no longer the main concern. What we're talking about is small and wide data. And why are we talking about small and wide data? Because it's been shown to prove to provide much more context, especially as it's related to machine learning. And we all know when there's more context with machine learning, you have less data-hungry machine learning, right? So there is a reason why knowledge graphs are becoming very important in this. Now, all these are complex forms of data, and they can only be analyzed using graph technology. So that brings me to the second element, and that is graph. So when data gets ingested into a property graph store like Neo4j, data and relationships are stored together. What that means is that you have, when you traverse a graph, you can find data as quickly, you can find relationships as quickly as you can find data. But relationships have a much more important effect. Relationships provide the first level of context to data, and we call this dynamic context. Because when you take data and you throw it into a dynamic structure like a graph, you get a structure that's connected contextually to all of its neighbors. The neighbors are connected to their neighbors, and you'll see that the graph grows richer and richer as more data is added, right? So you're adding context dynamically. That's why we say graph adds dynamic context. Okay, and then the third element, and that's the organizing principle. Organizing principles come in many forms, and I'm just going to give you 2 examples. The first example is, a domain knowledge. The domain knowledge forms the organizing principle for an organization. What do I mean by that? If you're a pharmaceutical industry, you're involved with getting drugs to the market, right? And so there is this knowledge that's within the organization, within the pharmaceutical industry, and it could be in a very specific therapeutic area. It could be cancer, hypertension, diabetes, whatever it is. And that domain knowledge is very specific and proprietary to that organization. So that's an organizing principle for that pharmaceutical company. Okay? In more formal terms, we can also think of organizing principles as semantics. And what do I mean by semantics? Semantics just means, it means context, and it confers context to things, okay? So there are many different types of semantics, and shown here are 4 different types, and I'm just gonna walk you through each one of these. I'm gonna go from the simple to the complex. Okay, starting off with tagging, classification, and categorization. We all know what that is, so I'm not gonna go into any more detail. Following that, we have entity resolution and analysis. Entity resolution is all about determining whether records from different data sources represent the same entity, right? And entity resolution is important where consistency of data is key. For example, in the banking industry, you want to make sure that you don't have any clients committing fraud, and the way you do this is through entity resolution. All right, next we have controlled vocabularies, and they run the gamut from simple to complex as well. We have things like synonym rings or lists and taxonomies, and they're usually termed lightweight. And then you have the ontologies, which are termed heavyweight. And it's mainly because ontologies have better inferencing power. Okay, but again, for those of you in the audience who know about ontologies, keep in mind, when to build and maintain an ontology is very time and resource intensive. So, do it with caution. Build a minimally viable ontology so that you can get the most value out of it. Okay, and then last but not least, one last type of semantics is artificial intelligence. And of course, that covers everything from machine learning to deep learning, natural language processing, and natural language understanding. Okay, so these are all, I'm not going to go into any great detail about them to say right now. Suffice it to say that AI plays a very important role in knowledge graph completion, and this is a process by which missing entities and links are added to the knowledge graph using entity resolution and embeddings. Again, I'm not going to go into any depth about embeddings. You can catch a lot of talks this afternoon if you stop by the GDS sessions. Okay. All right. So, I talked about organizing principles. Why are they important? Because they add the second level of context to data. Okay. And so we say that knowledge graphs have deep dynamic context. And the thing I'd like to point out here is that context is what knowledge graphs bring. And, so if there's one thing that you remember from this session, associate knowledge graphs with context, context, and more context. And especially as we talk about analytics and machine learning, context becomes super, super essential. And that's why knowledge graphs are so important right now. All right. I've just talked to you, I've walked you through the basics of building a knowledge graph. What I'm going to do right now is shift gears a little bit and tell you why knowledge graphs are so exciting. Knowledge graphs are exciting because they lend themselves really well to multiple use cases across the data spectrum, from data management and data analytics all the way to machine learning. All right, so what we've done at Neo4j is we have figured out a different way of looking at knowledge graphs, and I'm going to hand over to Jesus to present this next part.
Thank you, Maria. Yeah, so, well, you probably have noticed that no two knowledge graphs are the same, right? They are in structure, in characteristics, but we have identified a number of common features that appear again and again. And that's what we're trying to analyze here, because we think that characterizing knowledge graphs helps us understanding them better. And we've come up with 3 main categories. I'll go over them in a minute. But they all sit on top of a common foundation, right? Every knowledge graph is probably the result of integration of data coming from different sources. And when you integrate data, you have to solve the problem of identity. You have to determine that this data, this element coming from this data source is the same as this one coming from this other data source. And that might involve merging them in the knowledge graph into a single node, or representing in some form that they are equivalent, that they are the same. So this is kind of the foundation on top of which the three categories. So these three categories, you don't have to think of them as probably a complete picture. I mean, we might be adding more, but I think they're representative. And of course, they're not mutually exclusive. That's very important. Any complex real-world knowledge graph implementation will combine many of them. Think of, I don't know, a digital twin. I mean, there will be elements of pattern matching, of dependency modeling, and even semantic search. But let me go quickly over each one of them. So the first one is, we call it semantic search. And it's based on the idea of, well, commonly, the starting point for this type of knowledge graphs is a collection of things. It can be a collection of documents. It can be a collection of product descriptions. It can be a collection of articles. And we want to enrich this representation of these documents with features about them. It can be annotations with entities that are mentioned in them. It can be any kind of classification. And then when we've enriched this representation, we're going to overlay a domain model like the ones that Maya was describing at the beginning. So we will overlay maybe an ontology, maybe a taxonomy. And by doing this, we are giving multiple paths for exploration, and we'll be able to navigate from the data to the metadata and back and answer very interesting questions. We'll get back to that in a minute. So that's semantic search. The second one is pattern matching knowledge graphs, and these are all based on shapes on your data. You can find, when I talk about shapes, a star, a highly connected node. That might be a central element in your network. It can be a piece of infrastructure that many things depend on, a single point of failure. It can be a ring, indicating an unusual way in which money is flowing in your data set that can maybe uncover some fraudulent behavior. It can be a chain of events that uncover a particular customer behavior that maybe can help you predicting churn. It can be a cluster. A cluster maybe identifies a set of related topics or a set of highly connected customers. So a chain, a ring, a star, a cluster, all these shapes are so easy to identify and uncover in a graph and so hard using other type of technology. So that's what pattern matching is based on. And the final category is dependency modeling. I think it's important in itself because it's all about representing, yeah, of course, dependencies, right? Think of a project, tasks. Tasks depend on the completion of other tasks. Tasks depends on resources, on individuals being available, resources being available. And the interesting thing about modeling dependencies is that when we provide the building blocks, like I know that this task depends on this other task, the graph will build a complete picture. That was interesting, unexpected anyway. Sorry. So by giving the building blocks, the direct dependencies, the graph will help us exploring and uncovering the indirect dependencies, the tricky ones. Right? Think of a telecoms network. Right? It's easy to say that when a router goes down, what incoming and outgoing connections are going to be failing, but what's happening to the higher level dependencies? What happens to the links that go over it? What happens to the services? What happens to the customers? So this is the kind of thing that's hard to uncover, and that these dependency-based knowledge graphs are going to help us uncover. Right. So that's the kind of classification or the main categories that we've identified. But let me quickly go over how every knowledge graph story begins, right? There's always data siloed, fragmented, being owned and used by specific applications. And each one of them provides a partial and incomplete but complementary view of the world or of your business, right? And there are implicit connections across data in these different sources. And that's exactly the kind of thing that we want to make explicit in the graph. From an architectural point of view, that can look, there's different options, right? So we can move the data into a centralized repository, maybe replicate that into a graph, and that's fine. I mean, in some cases, having a centralized repository is a good approach. In some other cases, maybe it makes sense to have the data maybe staying where it lives and just using the graph to provide a smart index on top of that data, some kind of skeleton, and then retrieving the data on demand in what's called a data fabric. So multiple different architectural approaches. But One important thing, and I want to spend one slide talking about it, that's kind of a not a byproduct, it's an important element in any data integration initiative, and it's the management of metadata. So it's very important to be able to control your data catalog, to control data lineage, right? So, and it's interesting, I mean, it's funny because we're going a little bit meta here, right? So we're talking about bringing data into a graph, but we can describe the process of bringing data into a graph as a graph. And that's not something that we've made up. I mean, these companies, as you can see, have been working on that for years. And the first one was AirBnB at one of our Graph Connects, I think it was 17 in London, where they presented their approach. So they did build what they called a metadata hub. So they model things like data assets, data sources, tasks, transformations that would aggregate, transform, modify data sources, data consumers. There were users that may be owners of data sets, consumers of them. And by building something like that, and they Lyft with Amundsen did something very similar, LinkedIn and Manta Technologies, and many of them have actually open sourced their solutions. So I invite you to, when these slides are shared, to go and have a look at those. But they're very similar. And I was saying that by modeling that, they can answer questions like, you know, which are the data consumers that I need to notify when something goes wrong, when a data pipeline fails. And it's important to have this kind of clear and accurate visibility over your data landscape as data ecosystems get more and more complicated. So yeah, just a quick word on this metadata management, and let me quickly go over the first of the categories. So semantic search. So like I mentioned before, the starting point is a set of probably most of the times semi-structured or unstructured set of elements, documents, for example, like in this diagram that you see there. And there's an initial step covered by what's called entity extraction process, which is an NLP task that many libraries do for you in a very efficient way. And it's basically reading the text in your documents and extracting the entities that are mentioned in there. So that's step one. And then the other one is overlaying, like I was mentioning, some sort of domain knowledge. It can be an ontology, and that can pre-exist. I mean, you can use standards. There's some of them out there, or there can be your own enterprise ontology. Then linking the two is a tricky task as well. It's what's called entity disambiguation. But the moment, and I won't go too much into the detail of that, maybe there's another session in the afternoon where you can come and discuss if that's of interest to you. But the idea is the moment you combine these two planes, like I was mentioning before, you're offering ways of exploring the data, combining the actual instances with your domain knowledge. And you can do things, you can not only do semantic search, as in looking for things instead of strings. We are no longer limited by doing a search on our documents based on the text that they contain, but on the entities that we've been able to identify, and also how these entities relate to each other. And I was saying that you can answer not only the question of semantic search, but also semantic similarity. And if you think of it, semantic similarity, maybe it's just a pompous way of saying, you know, a path in your graph, because what you're saying is this document is similar to this one because they share a number of entities. That might be simple, but you can even navigate your domain knowledge and say they have entities that are not the same, but they are connected because they have a common ancestor. That would be one case, right? And that's where this combination, and the light comes back, this combination of the data plus the metadata in the form of domain knowledge becomes really powerful. So that's exactly what NASA did in the lessons learned knowledge graph. And they combine data from thousands and thousands of documents from their missions from the 50s, which they were struggling to analyze and to run queries on. And they applied exactly, you can read on the case studies from our website. It's exactly this approach. So they run the entity extraction step, and then they overlay this domain knowledge. And they had a significant impact from the, from the economic aspect, but also they quantified in up to 2 years the time that they saved with this approach of exploring the data. Good. Let me move quickly into the pattern matching type of use cases. So here, like I mentioned, it's all about the shapes. What you see in this graph, it's a simple description of a job description and a candidate. A job description is presented as a set of required skills, and to the side of it, you have a candidate, an individual that has a number of skills, maybe declared in the resume, right? So there is an actual overlap between the two. There's a correlation between the skills of this individual and the skills required for that job. That might be a simple pattern, but this correlation is actually uncovering the fact that this individual is a good candidate for the role, right? It could be more complex, like I mentioned before. Maybe a job requires some programming language. My candidate knows Python, and I have to know that Python is a type of programming language, and that's the kind of domain knowledge that the ontology will provide, or our taxonomy. So it could be a more complex pattern, multi-hop pattern. But when we can identify and express, that's the powerful thing with the graph. It's very, very easy to express this kind of overlap and act on it. I mean, we can extend our graph and maybe materialize this new relationship, saying this guy is a good candidate for this job, or we can do any other kind of automated processing on it. So that's what we mean by the pattern matching based type of knowledge graphs, and it's all about surfacing and uncovering these valuable relationships. There's this great example by Zurich Insurance in Switzerland, where their employees were answering questions, calls about claims, and in the claim center, and they have a reduced set of field investigators who were looking at those claims for fraud situations, right? And it was a manual process, a very time-consuming, not very efficient. And what they tried is to improve that process by automating the first triage. So they built a knowledge graph in Neo4j, combining claims information with policies, with financial information, personal information about their insured individuals, the insured property, whether it was home or vehicles. And using that, they managed to, by applying exactly this kind of pattern matching approach, to significantly improve the efficiency of this triage phase. And I think they quantified it. It's in the case study, but they quantified it around 50,000 hours a year in the effort that these investigators had to spend on that process. So really valuable. From the point of view of the business value that it provides. I've touched on a couple of industries and case examples, but there's many others. I mean, think of retail. I mean, in order to provide relevant recommendations, we're looking at patterns. We're looking at behavior of customers that are similar to you, and based on that, be able to recommend or personalize your experience when you're shopping on a particular retailer. You can see also pattern matching applied to, well, I mentioned fraud briefly, but skills discovery as well, and in life sciences for things like patient journey analysis and literature discovery. This applies to linking to Maya's classification of data to highly connected data, of course, to many or one-to-many, and also the cases of hidden data. So. Yeah, just one final example to conclude, but this success story from DXC, especially in Australia, is where the team is based, where they were facing a challenge of losing employees, and that was all down to the fact that they didn't have an easy way to detect areas where these trained and experienced employees could be repurposed in a way, and what they did, of course, is they built a knowledge graph in Neo4j, and they applied techniques like the one I just described, and now they're moving from there to apply AI and machine learning to build predictive models, and not only be able to do this kind of matching, but also provide recommendations for career development. So not only they can match candidates or individuals that are maybe redundant in one area of the organization with other required jobs, but they can also uncover this kind of career path progressions that they can use to recommend, and also detect skill gaps in the organization. So really a powerful approach, and I'll probably stop here and hand it over to Maya again to continue with the last of the categories.
All right, thanks, Jesus. That was a very comprehensive overview of the different types of knowledge graphs, the pattern matching knowledge graph and semantic search. What I'll do is I'm going to finish up with the dependency type knowledge graph. And here, I think I need to wake the audience up a little bit. So I'm going to play a little game. Okay, so here you see a table that has about 15 elements and their dependencies. And I'd like a show of hands from the audience if you think there is a dependency between element A and element F. And I'm not going to give you too much time, 5 seconds. 1001, 1002, 1003, 1004, 1005. So please raise your hands if you think there's a dependency between element A and element F. I can't see those hands. I see a few. Okay, cool. Okay, excellent. So I have to tell you that this is a very hard task to do, and I didn't give you too much time. But really, if I just asked you to take a look at this table and give me a guess, it's a 50-50 chance that you're going to get it right. And the reason for this is because what your brain is doing is it's trying to connect element A with element B, and then you're going to see if element B is connected to F. And then again, A to C, C to F. And you're trying to do all of this in a very short amount of time. But imagine this. If you were to map this in a knowledge graph, you can see immediately that, I'm sorry to say for those who raised your hands, there is no dependency between element A and element F. Okay, and what I just described to you in the earlier, when I just talked about this, is you're trying to do it like you were in a relational databases. Your brain is trying to do those joins, and it's a very hard task to do. It's very time consuming, and here we only had 15 elements, and that should maybe that'll take you 5 to 10 minutes. But imagine if you had 1,000 elements. I would say it's a near impossible task, and Jesus always corrects me, and he says it's not impossible, but
it's not the most efficient way of doing it. Of course, there you go. So that's
he's always correcting me about that.
We've been doing it for 40 years. I mean, we've been modeling these kind of dependencies in relational databases, and what you've done is exactly, I think Maya has made you feel like a relational database doing joins and joins and joins. So yeah, possible, but not ideal.
Yeah, let's not join, let's connect instead. So let's do it with a knowledge graph. All right, okay, so this is a fun exercise, but what is the real business value behind this? And I'm going to use the building of a car as the example. Every car consists of about 30,000 components, and these components come from 4,000 odd suppliers around the world. And they go towards the building of 1,800 parts. Now, imagine if there's a single component manufacturer who shuts down, let's say in China, and I'm not making this up, this is exactly what happened when the pandemic hit. There was a single component manufacturer that shut down, and all the auto manufacturers who relied on that component were really, really impacted, right? And we know there's chip shortages because of that. So what I'm trying to say here is that one small single moving part affected or impacted the entire supply chain. And that's what dependency knowledge graphs allow you to immediately identify and be able to rectify that situation. And keep in mind, these may look like small dependencies, but they have huge, huge impacts. Again, this is why dependency knowledge graphs are so important. Okay, so what are some of the industries and use cases? Before I dive into that, let me just tell you what the data characteristics of dependency knowledge graphs look like. Typically, it's small and wide data, and either there are one-to-many relationships, but more often than not, you'll find that there are many-to-many relationships. That's where there's so many dependencies, right? You also find this kind of hierarchical and recursive data that plays a big role with dependency knowledge graphs. What are some of the industries? We have telecom, manufacturing, supply chain, but of course, again, keep in mind that these aren't the only ones. I mean, you could find other industries, for example, in the financial industry, and I'm going to ask Jesus to help me again. You have ultimate beneficial ownership. Did I get it correct? There you go. That's a use case. For some reason, I can never remember. I just know it as UBO, and I can never remember what the exact words are. But UBO is a great example of a dependency knowledge graph. In the pharmaceutical world, we also have track and trace, exactly what Jonathan Lowe talked about in the keynote with Emil, right, from Pfizer. That's another example of a dependency knowledge graph. Okay, so it's across all industries, except that you see more of it in the 3 industries that I've shown here. What are some of the use cases? Typically, you have root cause analysis, impact analysis, what if analysis. If you're trying to identify bottlenecks or redundancies, those are also good examples of dependency knowledge graphs use cases, as are track and trace and data lineage. Okay, so what I'm going to do right now is I'm going to actually dive into an example and share with you a couple of use cases, and I'm going to use the telecom industry as the industry to exemplify this. And the reason will be clear when I tell you exactly why. If you take a look at if you take a look at the telecom network, you'll see that it's made up of multiple layers. And you have the bottom layer, which contains the physical infrastructure. Includes things like routers or routers, as I heard Jesus say, and it's a British way of saying it, routers, devices, switches, so on and so forth. And then you have multiple logical layers, and the top layer is the services and customer layer, all right? So that's the telecom network. Now, there are hundreds to thousands of events that take place events per second that take place in a telecom network. And, and these events are generally interrelated within a layer, and they also have dependencies across many, many layers, okay? So you can see clearly that as soon as I talk about many, many dependencies, you have to have a dependency knowledge graph. That's the only way how you're going to be able to identify what these dependencies are and what impact they'll have, right? So there are two types of analyses we can do. We can do impact analysis and we can do root cause analysis. So I'm going to talk about impact analysis first. For impact analysis, we use either event prioritization or event filtering. And what we do in this process is we prioritize events based on the impact that they're going to have. And let's say, for example, there is a loss of signal due to a failed device. Okay, so what we do here is we look at that, the event that caused the loss of signal due to the failed device, and we, in the knowledge graph, we follow its dependency all the way to the top to see which customers or which services have been impacted, and then we can take the right remedial action, right? So this is a true example of a bottoms-up analysis, where you start at the bottom infrastructure layer and follow the dependencies in a knowledge graph all the way to the top to identify the impact. Next, we have root cause analysis, and for root cause analysis, we use event correlation. Here, I'm going to give you an example of, let's say there's a failure of service, right? Whenever a failure of service occurs, it's not going to occur as a single event. It's actually going to occur as multiple events, and these events will either take place simultaneously or very, very close to each other. So what we do in this case is we group all of those as symptoms, and and then what we do is we follow those dependencies all the way down to see where they converge. And that point of convergence is is identified as the root cause of failure, right? So this is very much a top-down approach where you see events at the top layer, and then you follow those events to identify the root cause in the physical infrastructure layer. So I hope that's clear. And it's always good to see a customer story. And here what I'd like to do is share with you the US Army. And the US Army had a significant logistics challenge in buying and managing equipment. Okay, so what they wanted to do was to create this huge bill of materials, or BOM, and they wanted so that they could track every piece of information, okay? Every component and its cost, every part and its components, every piece of equipment and its parts, and then the lifetime, the lifetime of a piece of equipment, right? And they wanted to do this because Army leaders needed to, forecast the need for replacement parts. Army leaders also wanted to calculate the mean failure rate, mean time to failure rate of their equipment. And last but not least, and this is probably the most important, they wanted to, these Army leaders wanted to do complex what-if analyses to, to determine like the cost of deploying certain troops and equipment to a new war zone, for example. I mean, that's what the Army thinks about, right? And so those were the kinds of problems they were looking at. So what they did was they deployed dependency knowledge graph. And the results they got were stunning. One was that ordering of parts was quicker, cheaper, and much, much more accurate with the dependency knowledge graph than with the PLM system which is really a relational database that they were using previously. That was one thing. The second thing was complex what-if analysis, which when you really think about it is dependency analysis. Complex what-if analysis was 8 times faster, allowing the Army to be much more agile with their responses. And again, keep in mind, this is a US Army. You want to think about agility, and you want to think about quick responsive time, right? They achieved both of those with this dependency knowledge graph. So with that, I'm going to come to the end of the presentation. You know, when Jesus and I thought about this, we're thinking, what could we think that was big enough? You know, really thinking of go big or go home. You know, what was big enough that would cover everything that we wanted to talk about knowledge graphs? And we came up with the universe of knowledge graph. I don't think anything can be bigger than the universe, so I hope we achieve that. But on a much more serious note, I hope with this presentation you take home the fact that knowledge graphs are powerful and they're versatile. And if you have complex data in your organization, and it's not even if, we all know we have complex data, you should be using knowledge graphs all the time for all your complex data problems. With that, I'd like to stop, and Jesus and I are open to any questions you may have. Thank you.